All right, today's a big day for Algebra 2 students because today we start logarithms. Yeah, yeah. And not only is it logarithms, but it's also, unfortunately or fortunately, depending on your perspective, the last chapter of the academic year. This is it, the last chapter of the year. Oh my gosh. Okay. Now, we always study what's called a logarithmic function after we study an exponential function, and it's for a very good reason. A log function is the inverse, I'll just start off by saying, is the inverse of an exponential. Is the inverse of an exponential. So, like if you multiply a number by 5 and you want to get back, you can divide by 5. Multiplication and division are inverses of each other. What's the inverse of subtraction? Addition. What's the inverse of an exponential function? A logarithmic function. What's the inverse of a logarithmic function? An exponential function. They are each other's inverse, okay? So let's look at what the graph or the equation, first of all, of an inverse would look like. Let's say we have f of x equals 2 to the x. This is exponential, right? We know it's exponential because it has a variable as an exponent and it has a numeric base. Yes, this would be exponential what? Growth or decay? Growth, right? Times 2 times 2 times 2. The inverse function would look like this. It would be log, which is short for logarithm, L-O-G, and the little subscript there, we read this as log base 2 of x. That's how we read it. Now, it's not surprising that this number over here in the exponential, we call that base 2, right? That's the base. We call it the base. Over here in the log, we use the same number as a subscript, and we read it as the same thing, log base 2. Okay, so what do you think the inverse of y equals log base 5 would look like? The inverse would be what? 5 to the x. Very good. They are each other's inverse. And it works for decay as well. If you had log base 1/5 of x, the inverse would be 1/5 to the x. Okay, so the base is always the same. It just has a different location. It's a subscript on the log. Okay, now what do their graphs look like and how are they similar? We know that 2 to the x, I'll highlight it in yellow, 2 to the x might look like this. This is y equals 2 to the x. Okay? To get the graph of any inverse, and we talked about this year, to get the graph of any inverse, you reflect it across the line y equals x. That's your 45-degree line. So what happens with all these points if you reflect them across that line? Well, just turn your head at a 45. Harley looks like he's already doing it. Turn your head at a 45. And just imagine reflecting those yellow values straight across that dotted line. You're going to get these values down here, which I'll highlight in red. Okay. So these equations are as follows. This is the graph of y equals 2 to the x. And this is the graph of y equals log base 2 of x. And they're inverses of each other. Notice what happens to the ordered pairs. They just flip-flop around. So the point 2, 4 reflects straight across perpendicularly to the point 4, 2. The point 1, 2 flips straight across to the point 2, 1. You're just changing x and y. That's all you do for an inverse. Now, the consequence of all the x and y information exchanging is relevant because it affects the domain and range. For instance, this is the function 2 to the x. The inverse is what? Log base 2 of x. Good, 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 good. The domain of the exponential function was all real numbers. I'll make that a double bar R. The domain of the exponential function is all real numbers. That should turn into the what of the exponential? Wait, the domain are the x values, right? What are we doing when we flip across the the line y equals x? The x and y's switch. Yeah, I'll use your words. I was going to say flip. They switch. Okay? All of the x and y information switches. So if the domain of the exponential is all real numbers, and those are the x values, that should be the what of the log, the domain of the range. It's the range. It's all real numbers. Okay? And you can see because what happens is this. The horizontal asymptote on the exponential turns into a what on the log. What happens to a horizontal and vertical line? What happens to the x and y axis themselves? Don't they switch also? So this is what's cool. The horizontal asymptote, we'll call this an HA, the horizontal asymptote of the exponential, turns into a VA, a vertical asymptote at x equals 0, which is the y-axis. All of the x and y information change. So we'll do this too. We'll say x-axis. The asymptote on the x-axis for exponential becomes an asymptote on the y-axis for the log. It's a vertical asymptote now, okay? And let's do this. The range of the exponential is everything above 0. Those are the y values. That should become the what of the log. The domain is all x greater than 0. Or if you're going to write it in set notation, you can say the set of all x such that x is greater than 0. And then the last thing we'll look at, the reference point at 0, 1, which is right here. Make it nice and purple. The reference point at 0, 1 reflects straight across and becomes the x-axis point at what? 1, 0. Yeah, 1, 0. So let's make this notation as well. 0, 1 was a y-intercept. And when you flip it around, you get 1, 0, which is actually a what? An x-intercept, right? Literally all the x and y information just changed. All right, so let's go ahead and draw a new parent function, okay? So here's your new parent function. We're going to call this, let me see what they're going to do here. Log, I don't think we have any log decay. Yeah, maybe we do. So let's look at this. We're going to have two parent functions. We have y equals log base b of x. In general, we say log base b of x. Okay? If the base is greater than 1, it's going to be logarithmic growth. And here's what the graph looks like. Let's sketch the graph right here. Here's the characteristics you need to show. It has a vertical asymptote on the y-axis, and it looks like this, and it passes through the reference point 1, 0. That's what it looks like. Okay, that could be log base 2 of x, it could be log base 3 of x, it could be log base 4 of x, but that's what it looks like. All right, now there's one other version. What if we have y equals log base b of x, but now the base is between 0 and 1? If that were exponential, between 0 and 1 means it's exponential what? Decay. Guess what we call it now? Logarithmic decay. It's still decay. So here's what it would look like. It still has a vertical asymptote on the y-axis. It still has a reference point of 1, 0. But instead of increasing from left to right, it does what? It decreases from left to right. So those are your two new parent functions. If you get those memorized, you can handle any log graph. Okay? You're starting with a growth function on the left for any base greater than 1. You're starting with the shape on the right for any base between 0 and 1. The right could be log base 1/2 of x, log base 2/3 of x, log of 0.1 of x, whatever, as long as the base is between 0 and 1. Bless you. And what do they have in common? Let's highlight what they have in common. They have vertical asymptotes on the y-axis at x equals 0, and they have the reference point at 1, 0. That's what they share. Okay? Which means they share their domain and range. The domain is everything greater than 0. The range is all real numbers. The domain is greater than 0. The range is all real numbers. Okay. Let's complete the chart. We're going to be doing inverses. This chart is going to be the inverses of each other. That's what the name of the chart is. So if I have log base 3 of 243 equals 5, that's how we read that. Log base 3 of 243 equals 5. How are we going to write that in exponential form? Well, here's the way that we can go back and forth between the two. All right? The base is easy. The base is still considered the base in both of them. But a log is, at its very core, a log is an exponent. That's what a log is. A log is an exponent. So here we have the log equal sign, that means is, right? And then we have x, which is the exponent. What is a log? If you had to just tell someone what a log is, you would tell them a log is not only the inverse of exponential, but a log itself is an exponent, right? What's a log? A log is just an exponent. That's all it is. Okay, so over here, when you convert it to log form, you get log equals x. The log is the exponent, x is the exponent. So this, if you want to draw a double-headed arrow in between these two, I call this the conversion formula. It allows you to go back and forth between two things that mean the same thing. It's like sentence structure in your English class, right? You could say something like, when I do math, I get happy, right? But you could switch the structure around and say, I get happy when I do math. The message is the same, right? It's just the sentence structure is different. That's the same thing with these two things. They have the same components, A, B, and X. They're just in a different order. So let me go ahead. I'm going to go out on a limb here, and I'm going to introduce the real definition of a log, okay? Here's the log right here. This will help you understand what a log is. A log is an exponent, as we already said, to which you raise a base. This is how we define it in pre-cal. To which you raise a base to achieve a result. That's it. So it's not just any old exponent. It's a particular exponent to which you must raise a certain value to achieve a number. Okay, so here's what I mean by that. If you have log base 3 of 243 equals 5, you could say the log is 5, right? At its core, the log equals 5. The log is 5.
I'm just wondering, do you think we can be outside?
Yeah, we'll try it. I might be a little late getting there because I've got to get a few people set up with a quiz. But if we get there and we can't, then we'll just come back over here as a group. Okay? So don't fear. Go outside. Don't prop the door open. Just get at the picnic tables, and I'll be there to let everybody back in. Okay. So the log is the exponent. What's the exponent? 5. What's the log? 5. So here's what this means. 5 is the particular exponent to which we must raise the base is 3, to achieve the desired result of 243. 243, we call this the argument. The thing that we take the log of is called the argument, and it's our desired result. So we can say this another way. If 5 is the exponent to which you must raise the 3 to get 243, then that must mean that 3 to the 5th power is 243. Now, some people like to think about it this way. They like to think about converting it like going around the world. You start with the base, and you go around the world. So you go to the other side to get 5, and then you circle back to get 243. Some people like that. 3 raised to the 5th power is 243. 3 to the 5th power is 243. So guess what 3 to the 5th power actually is? It's 243. Okay? Now, without looking at it over here, let's see if we can write this equivalently in a log format, because they mean the same thing. If you're going to write this in a log format, here's how you would go the other direction. You would start with your base. The base is 3. So you're going to say log base 3. That's how you start. The base is 3. Now, the log is the exponent. The log is the exponent. What's the exponent over here? The exponent is what? 5. So you would say the log is 5. The log is 5. And what's the only number that's left? Well, the desired result is 243, which has to be right here. This is your desired result, which is also known as the argument. The argument is the thing that you're taking the log of. Okay, so that's how you go back and forth between the two. They mean the exact same thing. Okay, let's try it now on the next line. 4 to the negative third equals 1 over 64. That's a true statement. 4 to the negative third power is 1 over 64. But I can write it equivalently in log format by doing this. I start with the log. What's the base? What's the base of the exponent? The base of the exponent is what? 4. 4. And what is the exponent? The exponent is negative 3. So leave a little space and say the log is negative 3. The log is the exponent. Equals is the word is. And what's the only number that's left? 1 over 64. And that's a true statement in log form. In other words, we say log base 4 of 1 over 64 is equal to negative 3 because 4 to the negative third power is 1 over 64. They mean the exact same thing. When I do math, I have fun. I have fun when I do math. Same thing. All right, let's try going backwards now with this. If log base 6 of s equals r, then it's easy to go from log to exponential because you can do the around the world thing. So you would say 6 to the r is s. Easy enough, right? I don't like to teach gimmicks like that. That'll get you the right answer, but it's not really making you understand why it works, right? And I want y'all to understand why it works. Other teachers might just say, do the around the world, you got it, you're done. I want you to understand why it works. So let's understand why it works. The base is 6. Over here we call that the base, right? The log is the exponent. So if you want to go, the log is r, the log is the exponent. So there's the exponent. And then the argument, s, is your desired result. Okay? And now you understand why it works. All right, one last, let's go from left to right. If I have 1/5 to the w equaling v, then that's equal to, it's an equivalent expression to log base what? What's the base over there? 1/5. Leave a little space. I always like to leave a space and come back and do it last. If the log is the exponent and the exponent is the log, what's the exponent over here? W. So the log is w. And then what's the desired result? V, that's your argument. So we read that as log base 1/5 of v equals w. And you can quickly check by doing the around the world. Does it work? 1/5 to the w, does that equal v? 1/5 to the w, does that equal v? Yeah, it does. It does. You can't do the around the world when you start with exponential. But if you start with log, you can do the around the world and check. All right. It works. It works. All right. With the exponential expressions, we know that 5 squared equals 25. So we know log base 5 and 25 equals 2. Here are some examples. All right. So let's do these rapid fire. 3 to the 4th is, what do we do? We're supposed to do here. Oh, yeah. 3 to the 4th. What's 3 to the 4th? 81. Okay. So guess what log base 3 of 81 is? 4. Yeah, they mean the exact same thing. Log base 3 of 81 is 4. And here's how we would justify it. Log base 3 of 81 is equal to 4 because the base 3 raised to the log's power 4 equals the desired result of 81. Okay, if you want to use that logic, it's easier to go from log to exponential. It makes more sense to me. 3 to the 4 is equal to 81, so 3 to the 4th equals 81. All right, let's do it over here. What's 4 to the 3rd? 64. So guess what log base 4 of 64 is? 3. It's the exponent. The log is the exponent. Yeah, good. All right, what's 7 to the negative 2nd? Yeah, because that's 1 over 7 to the positive 2nd, right? We know how to get rid of the negative exponent. And that's the same as 1 over 49. So if I write that in log form, we say log base 7 of 1 over 49 is equal to what? Negative 2. Last one. The square root of 36 is the same as 36 to the 1/2, which is also known as what? 6. So log base 36 of 6 is equal to what? 1/2. The log is the exponent. 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 This is Korpi. I do. Front office real quick. We'll do. Okay. Harley, you're supposed to run down to the front office real quick. You must be there to pick something up. Okay. So the log is the exponent is the log. The log is the exponent is the log.
Are you multitasking? Okay.
The log is the exponent is the log. Now, why do we even need logs? Okay, let me tell you why we need logs. Logs are good for dealing with large numbers. Or small numbers. And when I say large, I mean astronomically large. When I say small, I mean really small, like microscopically. By using logs, when you have these huge numbers, it allows you to work with something called, y'all probably have seen this before, scientific notation. Have you ever heard of scientific notation? This is for huge numbers. So like if you have 3.45 times 10 to the 11th power, okay? What logs do is they look just at the exponent. And they're like, okay, I'm going to classify this number as log base 10, and all we have to do is look at the exponent now. The base is 10, and the number 11 is an indicator of its relative size. So if I had a number like 3.45 times 10 to the 17th power, all I would be doing is comparing their exponents, right? I know that the log in the first one is 11, the log in the second one is 17, so I know the 17 is bigger than 11, and I know that that number is bigger, okay? So what logs really do is they allow you to write numbers in scientific notation, but scientific notation always uses base 10. What logs allow you to do is to use any base, okay? And what you do is you look at the exponent itself as an indicator of its relative size. What if those numbers, instead of were 11 and 17, what if they were negative 11 and negative 17? Now it's the same thing, right? Now those are going to be microscopically small, and which one of them is smaller? The negative 17 is the smaller number because negative 17, the log, is a smaller number than negative 11, the log. So anytime you do scientific notation, that little exponent that's on the 10, that's your log, okay? And it allows you to talk about the relative size of the numbers without looking at the actual numbers themselves, okay? It's a really cool idea. All right, use mental math to solve the following. So this is really cool. We got f of x is equal to log base 4 of x. I know that's going to be logarithmic what? Growth or decay? Growth. So here's what I know the graph of log base 4 looks like. Here's the graph of f of x. I know it has a vertical asymptote right there, and I know it's monotonically increasing, and I know it passes through the point 1, 0. Okay, there's the graph of f of x. I want to know what f of 16 is. You got it. 16 might be way out here. I want to know what this y value is right there. Right? So let's plug it in. F of 16 is going to be log base 4 of 16. And now I want to evaluate that. So here's how you can evaluate it using mental math. The log is the exponent, right? So here's how you do it. You say 4 to what power is 16? That's how you work these problems. 4 to what power is 16? And what's the answer? 2. So guess what this number is? It's 2. If you notice the log function, it decreases very, very rapidly. It almost looks like there's a horizontal asymptote, but there's not. Logs do a great job of taming really big numbers because all we're doing is looking at their exponent. All right? Cool. Let's try this one. If f of x is log base 2 of x, another logarithmic growth, what's f of 0.25? Well, let's plug it in. That's log base 2 of 0.25. And we want to use mental math for this. So 2, you can do it like this. 2 to what power is 0.25? Well, this one might help if you write 0.25 a little bit differently. What's another way to write 0.25 as a fraction? 1/4. So 2 to what power is 1/4? Well, maybe I can write 1/4 like this. Maybe I can write 1/4 as 1 over 2 squared. Would that also work? Isn't 2 squared 4? And maybe I can even write that like this. Maybe I can say that's log base 2 of 2 to the negative second power, right? Oh my gosh, now look what I've done. Now I can use mental math and I can say this. I can use mental math and say, okay, 2 to what power is equal to 2 to the negative second power? Guess what the question mark has to be? Negative 2. Yeah, the answer is negative 2. In other words, 2 to the negative second power is 1/4. Okay? 2 to the negative second power is 1/4. Here's a little theorem. This is what I was going to kind of save until pre-cal, but it just came up. This is important. Log base b of b to the x is just, guess what? X. Yeah, it's just the exponent. Okay? And the reason this works is because exponential base b and logging base b are inverses of each other. So watch this. If I evaluate this from the inside out, I would say start with x. Okay, I'll start with x. I'm going to exponentiate it base b. But then immediately I'm going to turn around and log it base b, and those will undo each other because they're inverses. So you should be right back where you started, which is where? At x. Yeah, at x. So that's a very, very important property of logs, okay? So let's see if we can do that here. Log base 7 of x, again, that's logarithmic growth. If I want to know what f of the square root of 7 is, I can plug it in. I can say log base 7 of the square root of 7 is what? And now your mental math could say 7 to what power is the square root of 7? Well, here's my strategy. If I can write this as log base 7 of 7 to some power, I know it would just be that power. It's just the exponent. The log is the exponent. So let's see if I can rewrite this. That's log base 7 of. How can I write the square root of 7 as a power of 7? That would be what? 7 to the what power? So guess what log base 7 of 7 to the 1/2 is? It's just 1/2. Yeah. If you can write it as log base b of b to the whatever, that whatever is your answer. Because 7 to the 1/2 power is the square root of 7. Look, we could do that over here too. The first one was real intuitive. When I said 4 to the what power is 16, well, we could have easily written it like this. We could have written it as log base 4 of, what's 16? It's 4 squared. And now what's log base 4 of 4 to the blob? It's just the blob, which is 2. It's just the exponent. It's just a different way of writing it. Now let's come back and reinforce this inverse property too. If log base 4 of 16 is 2, it's because 4 to the second power equals what? 16, and that's a true statement. Yeah. Okay. All right, so let's talk a little bit about two bases that show up quite a bit for logs. Okay. If you use log base 10, it is common, it is so common, we call this the common base. It's so common, it's called the common base. And because it's so common, we tend to write it like this. We tend to write it without a subscript. You okay, Dave? Hang in there. This is what you see in your science class. If you've ever been in a science class and you've talked about like pH levels and base levels, have you ever done pH levels? Acid and bases, have you ever done that yet? No? Those are hydroxyl ions and they are measured on a log base 10 scale. Have you ever done light intensity? Light intensity or decibels? Have you done sound yet? Decibels? Decibels are on a log scale. Sound, light intensity is on a log scale. Okay? And they're log base 10s. If you ever see just log and there's no subscript, that's what we call it, then guess what base you assume that it is? It's base 10. It's the common log. You actually have, let's do this, you actually have that button on your calculator. Watch this, I'll show you. It's so common, every morning I get out of bed and I have a cup of coffee and I give thanks for the state of Minnesota. Every day. This is delicious coffee, and thank you, Minnesota, for giving us access to this fantastic standalone calculator that I didn't have before this year. Look to the left of the number 7. Look to the left of number 7. What do you see? LOG. Now, not only do you see LOG on that key, but what is the second function of that same key? 10 to the x, OMG. How are 10 to the x and log related to each other? It rhymes with pin verses. They're inverses of each other. That's why they're on the same key. So it's log base 10, okay? Now, there's another base that we as mathematicians like to use, and it's called the natural base, okay? So if you ever have log base e of x, where e is the natural base, we've already seen the natural base for exponential, right? Y'all remember what e is approximately? No, 2.71. Yeah, or 2.7. You can stop at 2.7. Everyone get a 2.7. It's a little less than 3. That's the natural base. It is also occurring so often that we give it a new name. And I always write it in cursive so that they stay connected. Ln of x is how we read that. We read that as the natural log of x. ln of x. It's from the Latin logarithmic naturalis. Ooh, that's fancy. Logarithmic naturalis. That's how it is in Latin. So that's where we get ln. Is that on your calculator anywhere? Yeah, it's to the left of the number 4. Look to the left of the number 4. You have ln. Hey, and what's the second feature on that key? E to the x, because e to the x and ln of x are what's of each other?
Inverse.
Not pin verses, but inverses. Y'all are good with hints. Yeah. So those are the only two logs that should ever not have a subscript written with them. They're the only two. Any other log that you want better be log with a number written as a subscript, okay?
If we put it, it will it like automatically go to a subscript, or like do we have to?
No, you don't even have it's pre-programmed. Yeah, so like this one, if you say log of 0.5, you can just type in log of 0.5 and it'll give you the answer.
What if you wanted to have a subscript for that?
Oh, if you wanted to have a different subscript on the calculator?
Yeah.
Okay, yeah, there is. I was going to show you all later, but I'll show you now since you asked. If you hit alpha window. If you hit alpha window. Alpha window is your F2 command, and there's a lot of choices in there. Look what number 5 is.
Okay.
It's log based. So if you go alpha, whoops, that's the wrong place to do it. Now I'm stuck in here. Let's go. Okay. So if you hit alpha window, which is F2 number 5, it'll give you a spot for whatever subscript you want. Okay. Yeah. All right. Good question. All right. Let's see if we can answer this one. It says evaluate each of the following to the nearest thousandth. Log of 0.5. Hey, what base is that? 10. It's log base 10. Do we have log base 10 on our calculator pre-programmed? Yeah, log of 0.5. Now, before I hit enter, which takes all the fun out of it, let's think about what an answer might be. We're saying 10 raised to some power equals 1/2. 10 to what power equals 1/2? That's what we're saying, right? Let's try 10 to the 0 power. What's 10 to the 0 power? 1. That's too big, isn't it? What about 10 to the first power? That's 10. That's getting too big, right? So it has to be less than 1. Yes, yes? Yes, yes. All right, so it has to be less than 0 too, doesn't it? Because 10 to the 0 is 1. It's too big. So the only types of numbers that are smaller than 0 are what types? Well, negative numbers, right? This has to be a negative number. Ah, there it is. It's negative 0.301. 3 decimals is the thousandth place. We knew it was going to be negative, though, didn't we? Because 10 to the 0 was 1, and that was too big. And so we had to make it smaller, so it's a negative number. Now watch this. Let's check it out. Let's check this out. If log base 10 of 0.5 is negative 0.301, then 10 raised to that power, you can recall the answer by hitting second negative. You see the little answer key on the negative button down on the bottom right? You can raise it to that answer with all the decimals, and what should we get when I hit enter? Do I get 0. Ah, it works. How do I do that? Okay, we have to do this first. This is how you recall it from the previous line. You hit 10, and then raise to the power of, you hit second negative. And it recalls the answer from the previous line, and you get 0.5. That's how you can check. Okay? Sweet. All right, let's do ln of 2. Now, before you hit enter, let's think about it. This is the same as log base e of 2, and we want to know e to what power is 2. So e to what power equals 2? Let's try 0. What's e to the 0? 1. That's too small, right? So it's got to be bigger than 0. What's e to the first? E, which is 2.7. That's too big, yes? So the answer has to be some number between 0 and 1. Let's see what it is. Hit ln of 2 and hit enter, close parentheses, and it's 0.693. 0.693. Is that between 0 and 1? Sure is. And we knew that before we started because we're starting to think like logarithms. Now, quick question. Has anyone here ever heard of, in your science class, the rule of 70?
No.
You never heard of that? The rule of 70 basically says if you want to know how long it takes for a population to double, okay, whether it's a population of wolves or a population of bacteria, roughly it takes 70 divided by the growth rate years. Okay, so if it grows 10% every year, what's 70 divided by 10? 7. It takes roughly 7 years for the population to double. Guess where the rule of 70 comes from? It comes from the fact that 0.693 is approximately zero point 0.7, which times 100 is, as a percentage, is 70%, and then 2 is your double factor. So if you ever run into the rule of 70 again, it's because the natural log of 2 is 0.693. Okay? All right. All right, let's look at example 5 and we'll call it a day in here. The acidity level, or the pH of a liquid, I told you, is given by the formula. The pH, which is its acidity level, is the log of 1 over H plus, where H plus is called the hydroxyl ion. It's the concentration in moles per liter of the hydrogen ions in the liquid. Boy, is this exciting or what? What's the base of this log?
10.
10. It's your common log. There's no subscript, so it's log base 10. All right? In a typical chlorinated swimming pool, the concentration of hydroxygen ions ranges from 1.58 times 10 to the negative 8, there's scientific notation, moles per liter, all the way up to 6.31 moles per liter. What is the range for the pH in a typical swimming pool? Okay, so here's what we're going to say. The pH level, is going to be between the following, okay? Let's go ahead and just plug this in right here. So I'm going to do log of, and I'm going to plug it in. I'm going to do alpha x, which is 1 over, and then I'm going to type in 1.58 times 10 caret to the negative 8 power, just like that, okay? Oops, not there. Scroll to the right. Come on, get over there. One more. There we go. There we go. How does that look?
Perfect.
Did I plug it in for H plus? Yeah, I hit enter and I get 7.8. So that should be on the low end, 7.801. We'll go 3 decimals. And on the upper end, I think I'm going to have to flip these around actually. Watch this. If I do it again, I can just hit second enter. Second enter recalls it if you want to do that. And then all you got to do is come over here and change this to 6.31 and it's still times 10 to the negative 8. Yep. I got to flip them around. Okay, the bigger number actually ends up being smaller because it's in the denominator, and then the smaller number ends up being bigger, so 7.199. Now, do y'all know what neutral is? If I can spell neutral right? I tell you? Or did you say Nutella? Nutella, that's like hazelnut spread. Yeah, neutral is 7. If something is a 7, it's neither acidic nor basic. If it's above 7, it's slightly acidic. If it's below 7, it's slightly basic. Okay? So this pool is slightly acidic. The scale is a 14-point scale. So you don't want a swimming pool to be too acidic. Otherwise, when you jump in, what happens? Your skin melts and you die. Right. But you want it to be slightly acidic so that it kills all the what? Pee-pee. That's right. Pee-pee germs. It's got to be slightly acidic so it kills all the pee-pee germs. And so here it is. Here's the appropriate level for the acidity of a pool. If you want to be a pool technician, you would take a sample of the water, and then you would drop some chemicals in it, and then you would put it on a little test, and it would show you on the scale where it lives. If it's bigger than 7.8, you drop alkaline in there. Alkaline in the pool brings the acidity down. If it's below 7.1, you shock it. That's what they call it. You shock it. You throw in some chlorine, and you shock it up to the right pH level. And now you can swim in there right next to your buddy who's peeing, and you're like, pee all you want, dude. The acid's killing it, right? I'm swimming in pee water, but I don't care because the pool has the right pH level. Way to go, logs. Way to go, all right? Oh, we didn't do this one down here. I forgot one. It's a good way to finish up. We'll wrap back around.
Wait,
Log.
all we have to write is that the answer? Like you have to write.
Oh, that's it. Yeah, that's all I wanted. Yeah. What's the typical range for the pH of a swimming pool? It's between 7.199 and 7.801. We're done. All right, now let's look at this one. This is log base 5. So here's what we're saying. We're saying 5 to what power is 8? 5 to what power is 8? Let's think about where the number is going to live. Let's start with 0. Is 5 to the 0 too big or too small? 5 to the 0 is 1, too small. What about 5 to the first? 5 to the first is 1. That's 5. That's still too small. 5 to the second is 25. That's too big. So it should be between 1 and 2. So log base 5 of 8. Let's type it in. Alpha window number 5, log base 5 of 8, and we get 1.292. There we go. Sweet. At least we can pin it between two integers, right? It's kind of nice to pin it between two integers. All right, let's test it real quickly. 5 raised to the answer's power should give us what? 8, and it does. Okay, cool. So there's your introduction to logs. Logs are very, very important. Most scientific formulas have logs in them. Ebbinghouse's law of forgetfulness, even in the social science. Y'all had Guilford. Y'all talked about Ebbinghouse's law of forgetfulness. It tells you that if you master something at a certain level but you don't rehearse it, then if you try it again later on, you perform worse. Guess what that is? That's all measured on a log base 10 scale. Yeah, it's all measured on a log scale. Ebbinghouse's law of forgetfulness. Okay, we're done. Now, unfortunately, because we did TSI testing, your homework has to be due the next class day, which is when?
Monday.
Monday. Okay. So your worksheet or your homework is due Monday at 9 a.m. We don't have a whole day in class to work on it anymore. We're going to start 14.2 on Monday.